Good. All right, I came here to talk about Kubernetes the hard way. I thought at the beginning that we would actually have interactive questions, but it turns out we're not having that, so please log into the Slido thing. And if you didn't take the code from the slide, please ask from your neighbor or so on. So let's collect all the questions, and then we can come back to those in the end and go through them. All right. Buttons. No. Yes. All right. Who am I? I'm Martti Leppänen. I'm the DevOps team lead here at Smartly. So this is our office. I've been a sysadmin more or less for about 20 years. I ran my own IT consulting company for about 10 years or so. And the last 4 years of my career, I have been here at Smartly doing DevOps stuff. I started as a regular DevOps person. We actually didn't have a DevOps team at all. It was just development teams, and we were doing stuff. And then gradually we became more professional, and here we are. And the last 2 years here at Smartly, we've been doing Kubernetes in different ways. We've been trying it out, and now actually it is live, and we have a few fairly big Kubernetes clusters running on bare metal. Personally, I like to tinker all kinds of things. I like to understand how things work. I like to disassemble things and assemble them, and figure out where all the why do I have so many screws left after building it. So that's what I like to do in my free time. So, why would you do Kubernetes the hard way? Why would you run it on your own hardware or somewhere hosted hardware instead of buying the Kubernetes solution yourself? As you can see in the picture, there's a lot of impression that running your own kube cluster is a messy thing, difficult to adjust. There's a lot of knobs here and there, and my opinion is that this is not true. It's actually very simple, and the reason to run Kubernetes like this is that there's a lot of power and control that you get when you can run your own cluster and you can define your own way of doing things. You can have clear view to the system through monitoring, and you can have the ability to change the monitoring to whatever service you might want to use instead of being forced to use some platform that is pre-made for you. You can, of course, easily utilize other hardware, such as GPUs, and you can save quite a lot of costs if you do a lot of computing. So in the cloud, depending on what you do, some things are expensive and something not so much. So you can have I/O heavy load and GPU heavy loads quite easily if you're hosting your own cluster. And of course, still, this doesn't prevent you from using the cloud for dynamic scaling. Kubernetes is brilliant in the sense that you have these manifests that are fairly standard, and you can just put them out. It doesn't really matter that much what's lying underneath the system. And of course, when running on your own hardware, you can have security through encrypted communications. You have your own firewalls. You can have a very, very good view and control over what data goes where, which ports are open, and you can be sure that all of the data you're sending in and out inside the cluster and outside the cluster is being encrypted whenever it's needed. And of course, running your own kube cluster is worth doing just to understand how Kubernetes works. So Kubernetes is a fairly complicated beast. There's a lot of parameters, and understanding all the components, key components in Kubernetes is essential to even running it in the cloud. If you want to have any scale, you have to understand what's happening in the background. What does the API server do? So just practicing and deploying Kubernetes on EC2 even is a brilliant way to start, brilliant way to learn how it works and what the components are and what they do. All right, how do you do this? Empty slate. Kubernetes starts with etcd. So you have to have an etcd deployment to be able to have a state in Kubernetes. It's using etcd because it's fairly safe. and you can rely on it to have consistent data even in very, very poor situations. etcd is a known factor. It's easy to deploy anywhere, and for Kubernetes, there's really not much in terms of requirements, except that you have to use the newest version of etcd protocol these days, and that's it. Then, of course, you have to have the Kube API server, which is the part that listens to the internet and relays the commands you send to it to the rest of the Kubernetes system. It's a fairly simple program, but it's quite necessary to run, and it's important to have all of the certificates and all the connectivity set up in such a way that you can rely on it to be safe from the internet, and of course safe from you have the correct credentials and so on set up to work through this. But that's not yet where we are. Then we need the Kube scheduler. The Kube scheduler is another quite simple piece of software that monitors all of the nodes and resources you have available and schedules the stuff you want to run on Kube into different nodes. And scheduler takes into account a lot of different metrics from the nodes, what resources we have available, what is running where things should be balanced, if a node is offline or has some restrictions, some labels that need to be followed, the scheduler takes care of that. And then you have the Kube controller manager, which in reality is the most complicated piece of software in these three that I now listed. So this is running all the controllers. It's running the replication controllers, endpoint controllers, service account controllers, and others are all run in the same binary Kube controller manager. And this is more or less the heart of Kubernetes, where the manifests are dealt with and processed. But again, not a very complicated piece of software in terms of it's a binary, you run it, it has a few options, and you can easily start it up, for example, with Docker, or you can run it even as a service, and it still works. Yeah. And these three, and the etcd consists, or they make up the master node, which Kubernetes needs a few of to be able to work in different network conditions and different adverse situations where you might lose a computer for whatever reason. So we need a few of them so that etcd stays alive. You can also separate etcd into its own machines if you want to, or you can run it in the same master as everything else, depending on what kind of workload you're running on Kube. You might want to do it, or you might not. Then, in addition to masters, we obviously run Docker somewhere. Kubernetes is supposed to run containers. You can, of course, run other OSI-compatible runtimes than Docker, but Docker is what we're using here and what I'm going to go through today. So Docker, again, is a fairly simple binary. It has some requirements from the kernel. You have to run a fairly new distribution to be able to run a recent version of Docker. And there's you definitely should be running a new version of Docker because it's being developed quite at a pace, and any older version are quite buggy. In addition to Docker, you want to have the kubelet. And kubelet is on the nodes, the heart of Kubernetes, that takes care of starting up the services and making sure that everything is run correctly through Docker or whatever container system you have. Kubelet also, in addition to communicating with the API server itself, it starts up and it starts a few predefined pods that you can set up to it. And I will go through them a little bit later, but the kubelet both communicates with the API server and gets more stuff to run from there and talks to the API server, informing that here I am, please add me to your register, and so on. And then as the third part for the node, we have kubeproxy, which is taking care of the networking for the node. So it takes care of networking in the sense that where do requests go. So it follows up on which pods have which IPs, and it then routes the requests in the correct place depending on how you have set them up in the manifest. So each node needs to have a kubeproxy. The kubeproxy in reality has two modes of operation underneath, and this might be relevant if you run your own cluster. So it has the IP tables mode, where all of the traffic shaping it's doing is written into IP tables, and IP tables takes care of moving the packets to the right endpoint. And it has the IPVS mode, IP virtual server, which is a new Linux kernel feature, or reasonably new Linux kernel feature, where you can have another way of defining how load balancing is done between different IPs and so on. And this is the preferred way to run kube these days, because IP tables turns out doesn't scale into infinity. It only scales so far, and IPVS can be brought much higher, so into tens of thousands of pods and thousands of nodes. Then, of course, these things need to communicate somehow. The kubelet is using SSL TLS to talk to API server. It doesn't necessarily need much more than that. So you have to have some kind of certificate set up. So you can have, normally you would have your own certificate authority, and you would generate certificates for each of the kube nodes and the master to be able to have secure communications between them. And when you're running self-hosted Kubernetes, you might not have the luxury of having your own internal LAN port. So you can treat all communication between nodes as potentially someone listening. So everything that goes between nodes and goes between the master needs to be encrypted to be able to be safe from potential attackers. Then, of course, just communicating to the API server through TLS is not enough. The nodes need to be able to communicate with each other. There's a lot of applications on top of Kubernetes. And for this, we are using, and what I'm going to be talking about, we're using Weave. And Weave is another, it's basically a program that it acts as an interface for mostly IPsec/ESP. So you can configure a set of encryption keys and a set of way of discovering nodes, and Weave will then take care of the encryption and enable communication between the Docker containers. And it's used both for communicating with the master, not the API server, and with communicating between the nodes for whatever purpose you might need. Of course, it's not quite that simple. So while one node has these three basic servers, you have a kubelet, you have Docker, and you have kubeproxy, and this basically brings up Kubernetes. You don't have to have more than this. In reality, you will end up having a little bit more. You have to have some method of each node to be able to resolve DNS names. We are using Unbound. We used to be using DNS mask for this. And this is acting as a proxy between core DNS and services using the DNS server, so the node itself. So you can resolve host names that are generated within Kube in core DNS, and then you can also resolve, obviously, outside external DNS names to be able to communicate with the internet. And Unbound is a good tool, but there's obviously Kubernetes is modular. You can use a lot of other things too. This is what we were using, and it seems to be working quite nicely. Then of course you need a firewall of some sort, because if you have just a computer on the internet, you might want to have a little bit security in terms of what can be communicated where. You might not want the nodes to be able to accidentally talk to each other via an unencrypted way. So you want to have a firewall between the nodes and within the nodes to be able to make sure that your node is using the correct protocols and the correct ports to communicate. And obviously, you'd have to have some facility to be able to gather metrics from the node and gather logs from the node to have an idea on what's going on the node. It's quite important when debugging things that you have some method of knowing the system resources, also outside the cube, and knowing the system logs. Let's say your, I don't know, hard drive is broken. You have to have some method of detecting that, because cube, in reality, in itself doesn't know or care about the system logs and what happens underneath kubelet. So these are basically the very minimum of system services that you will require to run on a worker node. Then, in addition to those, somewhere in Kubernetes you have to have Weaver running, which then would create the Weave network, which I talked about earlier, and we'll come back a bit later. So that can be run as a Kubernetes pod. So you can just put in a manifest into Kubernetes and say that yes, all of my nodes need to be running Weave, and this is the settings that you put into it, and that's quite straightforward to configure, even though it's quite easy to make mistakes. Then you need the core DNS, which I talked about earlier. So Kubernetes relies on the ability to have DNS names resolved within the cluster. You have to have a DNS server that is able to know which pod and which IP has which name to be able to communicate between different pods and different services within Kubernetes. But core DNS in itself is not recommended to scale to every single node that you run. It's very inefficient to run multiple master servers for DNS, so it's convenient to have an unbound or some other DNS proxy in between, so that the core DNS itself is only doing mostly changes, and then other services used for the resolving on services. And core DNS doesn't have to run on all of the nodes. And then obviously in pods as well, you have to have some method of gathering metrics. You can have Prometheus running as a pod, or some other system that gathers metrics from your Kubernetes system itself. So you have to have, or you definitely need to have ways of monitoring kubelet, monitoring Docker, monitoring Weaver, and all of those services you're running. And one of the, I think, de facto ways at this point is use Prometheus, which then scrapes information and can store it into a database somewhere. And this is pretty much it. The master doesn't need any other services than I previously described, and the nodes themselves don't need more than this. And all of these can be, if you're reasonably well know what you're doing, these all can be set up in a few days, and then you can start to debug what went wrong. All right, let's continue to what is Weave. So I described earlier that we have this encrypted network between nodes, and we are using Weave, and we've been using Weave for quite a while. On paper, it's a very, very nice system. You can use to configure the Linux kernel-based ESP packets, so you can communicate between nodes with a known security or reasonably well understood security and with good speed. So a lot of the other VPN solutions might be slow when you have a lot of network traffic and you want to transfer gigabytes and gigabytes of data. You might run into issues that encrypting is suddenly quite a large bottleneck. And Weave does this well because it's able to use the fast data path system, which is utilizing the kernel level data systems. And then, of course, in Kubernetes, Weave also does IP address management. It talks to the Cube API server and is able to know what the address pool Weave itself has and what Cube wants, and it distributes the addresses to different nodes by itself. So it's able to configure itself such that each node has automatically a certain set of addresses, and it keeps track on what addresses are where, so that you can easily communicate between the nodes. And due to this, it also has some firewall capabilities, and it can implement Kubernetes network security policies, which is very convenient, so that you can have more security also within the queue, so you can define which services can talk to other services and which cannot. And this is an important feature that is actually quite recent. And of course, Weave scales to hundreds of nodes, so it's easy to use, at least up to a few hundred nodes. But it's quite unclear on where actually the scalability ends and what you have to do to be able to transfer huge amounts of data between nodes to be able to make it work. And through that, there's some reality checks for this advertising speech. So Weave is quite nice, and I like it a lot, and on paper it's very nice, but it does have some issues. So each Weave service requires to have a database file on each host it's running on, and this database file contains the information on where each IP address is and how to communicate with it. It would be very wasteful to communicate this information all the time, so all of the nodes have to have a cached database for this. And in addition to having a file on the hard drive, you also have some kernel assistance. So the kernel itself will get a bunch of parameters, keys, and different information from Weave to be able to establish the encrypted communication between different nodes. And this data, in case Weave, for example, crashes, will stay in the kernel. There's no one to go and clear it out, and this can be surprisingly difficult to find, as we have found out. There's some other issues that are still kind of unclear. Adding many nodes, new nodes to Weave at once is not very reliable. So if you have 20 new nodes to a Weave cluster at the same time, then you might have some issues, because they're trying to communicate with each other and tell which addresses went where, but it doesn't necessarily work. So at the moment, we are at least recommending to run Weave in a way that you try to avoid adding new nodes. So this is not a problem if an old node comes back, it already knows something about the cluster, but if you add a new node, it has to communicate with the cluster and reserve a certain address block and so on, and this process is currently not very reliable and can break the network in different ways if you try to do that. And of course, Weave needs to have enough resources. It's running as a pod in Kubernetes, so you can give it one CPU or two CPUs or 5 CPUs, but it needs to have enough. At least one CPU would be good, because if it, for whatever reason, starts to starve of resources, it will fail health checks quite easily. It's actually recommended not to run health checks on these, because terminating the pod has side effects that you really don't want to have in your cluster. And of course, these host network access, because it needs to talk to the kernel directly to be able to configure the IPsec and configure the network interfaces that all of the other pods are using for communication. And it doesn't have very good debugging interfaces. So you have basically a very simple command line utility to the state of the system in, and you can do some simple stuff, such as removing one node, which you first have to know which node you want to remove, and other things that can be quite painful. But it's not bad. After you've got it running and you've taken these things into account, it does work, and it does handle quite complicated stuff such as network partitioning and other things such that it doesn't actually break itself. And we've done a lot of testing, and we've yet to ever break production with this. We've only managed to break weave in testing systems and when tinkering with different options and trying to learn on what the actual limits are. So for now, it's worked quite fine, but it's quite important to take these things into account when creating your own cluster. If you want to have a production-grade system, it's better not to repeat all the mistakes that other people have made. One of the nasty things we've had is that our development Kubernetes cluster, which is about 80 nodes at the moment, we had to entirely restart the cluster because we were unable to find all the persistence that we've had. It had very well hidden itself somewhere. We had to remove all of Weave, and we had to reboot all of the computers and reinstall Weave, and then have basically a start from scratch system to be able to get Weave back up and running. And this took us some 2 days to debug on why it's not working, and also quite some time to actually be able to get the cluster back up and running. Of course, this normally shouldn't happen. If you run your test correctly and you know what you're doing, you probably shouldn't be hitting these issues, but it's quite important to hug Weave a little bit and say happy words to it so that it stays happy. All right. Those are basically the basics on how to run a cluster on self-hosted basis. You can have working Kubernetes systems with only the components listed before. So that's enough. You can install those, and then you can already do some simple things within Kubernetes if you have all that up and running. It's not that complicated. We run a few Kubernetes clusters. They're quite large, or at least for us they're quite large. We run a development Kubernetes cluster which has thousands of pods, and all of our developers have access there. They can create their own namespace and run our application there. And then we have a production named Kubernetes cluster, which is able to host reliably almost all of our stack here at Smartly. Not quite everything, but quite a large part of all of the stateless application. And speaking of state, statefulness in Kubernetes is difficult. We've taken the stance that at the moment in production, we're not storing state. We're not storing persistent state on disk at all, except for Weave, which does, but other than that, no. So how to get around this? We're utilizing connectivity pods. We are communicating obviously with different databases. We have Postgres, we have Redis, we have RabbitMQ, we have Mongo, and all these things, and we need to be able to communicate with from the application to different databases and different places to store the state. And at the moment, what we're using is connectivity pods. So, for example, for Postgres, we have Pool, and for a bunch of services, we have AJ proxy, and you can run many of these replicas in a Kubernetes system, such that even if you lose a node or if you do some upgrades, you will always have the connectivity up and running, just as you would in a non-Kubernetes scenario. And Mongo and some other databases obviously have also their own way to connect and proxy the connections to the right servers. And for example, for Mongo, we're using Mongo to do that. We are running some in-memory services in Kube, which might not be advisable, but we've ended up doing it. With Redis, for example, we've run some 5-pod stateful sets, which are all in memory. They don't write anything to disk, but they do hold the state. So even if you upgrade a cluster or your node goes down, you still have 4 nodes left, and you have enough of a quorum for Redis to be able to copy its own memory and bring itself back up. This works fairly well, but there are situations where you might end up losing all your data, which obviously can happen with an in-memory database anyway, but for the most part, it's been working okay. It's not okay for larger data sets. If you run huge caches or some very large amounts of data, then it might not be the right solution for you. But small in-memory cache, it's okay to run within the queue. And for the development cluster, we are running Rook.io, which runs Ceph, and this actually adds disk persistence to nodes and creates this volume service, and you can request a volume for let's say a database to run the database inside the development environment and not lose all your data whenever you do some upgrades or whatever. But it does have serious downsides. At the moment, as things are, I would never run this in production. It's quite slow. It's not very fast for anything. It's an object-based storage, so running disk operations on it can be quite slow. And it's also, turns out, it's not been very reliable, probably due to the fact that we don't have an internal network connecting the different nodes, but it's using the weave.net to be able to communicate with other nodes in the Ceph cluster, and that has turned out to be quite difficult. This is quite likely the reason why we had the before mentioned crash of Weave, and we had to reinstall almost everything, and had some downtime for our poor developers who couldn't at that point run their own development environments in the cluster. But there is potential in statefulness, so even though it's hard, with some trial or error, you could definitely have some state there. You probably have to have some understanding in your application what the actual risks are. You have the volumes, there is disks available, it's just that you have to more or less, at the moment, manually be able to manage what data goes where and how the persistence is handled in a way that you don't lose the data you don't want to lose. But it's not very advisable to run, let's say, Postgres directly without other means of making sure that your data is being saved. Which is why we're running Postgres through PG pools, so we have an application pod or many application pods in our system which communicate with a bunch of PG pool instances, which are also pods in the system, and they in turn use SSL connectivity to Postgres and are able to detect themselves which Postgres is the master and which is the slave, and then either sending all commands to Postgres master or then doing some load balancing. So if you're doing select operations, for example, you can do selects on the slave as well if that's what you want to do. That might be sometimes a little bit more scalable depending on what you're doing. Obviously, for these things, make sure you have enough capacity. So when you have a bunch of connectivity pods, you have to understand that sometimes you lose a pod. Maybe a node goes down or something else. You're doing upgrades on a cluster, you lose a pod, and then for a moment you only have, let's say, half the pods if you had only two. So you have to have enough capacity to be able to handle some missing pods. And basically at least double the connections that you actually need. You need to be able to support. And of course, you can label your nodes such that you have connectivity nodes. You can have a few or many or 100 nodes that actually have connectivity to this Postgres instance. So not all nodes necessarily need to be able to connect to your databases. You can have a bunch of nodes and you can label them, and then PG pool is able to find the nodes that it needs to run on to be able to work. And if your service, Postgres obviously supports SSL itself, but if your service, let's say Redis, doesn't support SSL, you can also use a separate tunneling program, such as Ghost Tunnel or some other tunneling program to be able to do this SSL verification from a pod and then do this same kind of connectivity. I won't go into those details here, but I'm more than happy to answer your questions about it. But this has been a reasonable way to run connectivity from the Postgres cluster and to be, from the Kubernetes cluster and to be able to have state somewhere outside of the cluster. Then, we have a bunch of sensible defaults that come with Kubernetes. It's very important, and I can't stress enough to read all of the command line options that you have available for the services I mentioned earlier in the slides. So all of the things, kubelet, kube API server, kube controller manager, all of these have a bunch of command line options which you need to check and you need to understand. So the API controller, for example, has a limit of untitled requests. How many requests can it have open? And the limits by default, if you don't set anything, are fairly low. And it will be very interesting to debug if you're wondering why your cluster is slow, but everything seems to be working. And sometimes things just go into a queue somewhere, and kubectl commands take forever, and you have no idea what's going on. So understanding these parameters, there's good documentation for it. Understanding them and setting them high enough to be able to handle your particular workload and your amount of pods is quite important. And the same obviously goes for scheduler and the other components. So queries per second and how fast, for example, if you have a failed node, how fast do you want to have the pods evicted from that node? Maybe a node fails only for a minute. You don't want to move all the pods away immediately because then you'd have to move them back next minute. And this would cause unnecessary load on the cluster. You have to understand the application and applications you're running and tune the parameters through that. And this is one of the advantages too. So you can scale your cluster. You have a very large Kubernetes cluster when you know these parameters and you're able to tune them. When you're using, for example, Google's Kubernetes containers, you're not able to go into these parameters. And they might do what you want or they might not. But you can't change them no matter what you do. So it's quite nice, and this is one of the advantages of running your self-hosted Kubernetes. And as said before, you have to have high enough memory and CPU limits for all the call services that Kubernetes is depending on. So if you have the DNS crash all the time due to OOM killer going on and killing it, that's very inconvenient and can cause havoc in your cluster. And sometimes it can be easy to find if you happen to search for the right place, but sometimes it can be also quite difficult to debug. So going through the defaults in all the applications is important to have a reliable cluster and scalable cluster too. Load balancing then. When you get with a cloud system, you get elastic load balancing or Google Cloud load balancing. This is something that you don't get easily with self-hosting Kubernetes. So you more or less have to have some form of load balancing in front of you. You can do it without. You can open up your ingress to the internet, but this might have other side effects, and you might have things running in your queue you don't even know about. So my recommendation is that you have something in front of Kubernetes, that you have some level of control on what goes in, what goes out from queue. For us, we're doing quite a lot of manual work to be able to configure the different routes and different paths on where applications need to be found. It offers us some control, but obviously it increases overhead. It's not fun for a developer to come to DevOps team and ask for a certain path in the URL to redirect to their kube service. Some of it can be automated. We're not quite there yet, but for example, with console and SRV records, you can automate this HA proxy configuration in a way that developers themselves can have more control on where actually the service exists and what URL is listening to, and then you can have a more dynamic environment. And obviously, if you're running multiple Kubernetes clusters, then you can have the load balancer shift the request to the right place according to the configuration, which is also a very nice benefit. And we're also using dynamic DNS for the HA proxies, so that if for whatever reason some load balancer is down, we're not serving that particular IP address from the DNS, and we can be quite sure that our HA proxy cluster is up and running and all the services that are there are reachable. And of course, HA proxy itself has health checks and does check that Kube server on the other side is also running. So if you lose an ingress node, for example, for whatever reason, HA proxy is able to disable that particular ingress server and then move the requests somewhere else. A couple quick things still. Just to reiterate that you need monitoring. It's very important to have monitoring in the Kube cluster to understand what your resources, how your resources are being used. Do you have more of them? How much CPU do you have available? All of that stuff. What's going on in the cluster is very important to know. So what we're doing, this is just our recommendation. What we're doing is we're running Telegraph on the host for getting metrics from the system. And it monitors different host metrics. It's basically all of the system metrics are going there. And it also serves as a receive endpoint for statsd data. So we have legacy applications that send statsd information, and they've been doing that in the bare metal type running before Kubernetes. And that's a nasty piece of where you had to change how you send for different applications. So we brought this support to Kubernetes as well, so you can just simply, from any Kubernetes nodes, you can send to the local statsd service, and it will then send to our metrics database, and everything works just as it used to in a traditional app server type system. So it makes the migration path a little bit easier. Then of course you can run, as mentioned, Prometheus, which then scrapes different services, and you can have Kubernetes know all the endpoints that Prometheus needs to be scanning, and it scrapes the information and puts it into a database, and it's quite easy to set up and use. And Grafana is our way. This is a screenshot of Grafana of actually our developer cluster or production, I'm not sure. Actually, I hit it from there. Anyway, we can see quite nice dashboards on how much we're using of what, and very, very complicated queries even, and have a good overview of what the system is doing. And in Grafana, you can do simple alerts. You can say that if this goes over 10, then please send an alert to email or SMS or whatever you want to have. And for advanced alerts, we're using capacitors, so if you have to have a more complicated tool set, you want to have a derivative of something, and you want to compare it to something else, and you want to have some more logic in what actually consists of an alert, which is quite a few of the alerts. Not everything necessarily should alert. Then we have a system with capacitor to be able to do that. And that's the metrics database behind all of this. We're using InfluxDB. In addition to metrics, you have to have logging. In Kubernetes, it's fairly straightforward to be able to run. It's not very different to any other application server you might run. So we're using FileBeat to read the log files that come in, and it keeps track. And all of the Kubernetes pods are writing this std out, which then goes to a file, and FileBeat is able to read it. One of the things that you need to take into account to be able to rely on it is that you should monitor for any pods that are very spammy and might get your log pipeline stuck because of being extremely verbose for whatever reason. You should at least notice that this is happening. Go tap the developer on the shoulder that something is probably not quite right. And metric speed for reading Kubernetes events, which are the events that, let's say, a pod starts up, pod shuts down, and all that stuff, and to be able to debug different situations. This is important to save somewhere because Kubernetes doesn't have a very long memory of these events, and it forgets in a few days what actually happened because ECD is not meant for long time or large amounts of data. And obviously audit log to be able to see who did what with kubectl, what was being done, and you have to, of course, here to be quite careful and not to be too verbose if you turn on audit logging, it can be extremely verbose very quickly and bring in so much logs that you never ever had. And for storing all this stuff, we're using Elasticsearch, and for reading it, most of the bottom. And one more thing, as the last slide, you should be doing testing. So, as said, we've had some meltdowns, not with production, but with testing systems or semi-testing systems such as our development cluster. Every single change we do to our configuration as code type system, which brings up our Kubernetes cluster, we test it first by creating an AWS cluster, installing it the same way we would do with hardware, testing that it works, putting up a pod there, testing that everything is okay, and only then do we actually start thinking about deploying it into either our development cluster or production cluster or so on. And running multiple clusters, as mentioned, it's very good to have some other cluster than production that has a lot of load, so that you can see that what scales do you need to have, tools and parameters maybe, or maybe there's a problem with transferring too much data or something like that can come up, and it's very advisable to have another cluster that you can at least try to figure out if everything works as supposed to when you have a bit of load. And of course, it's good practice to deploy a new cluster every now and then. Maybe something goes wrong badly, you didn't expect it. It's the unexpected errors that are difficult, and it's really good to have the ability to bring back a new cluster from your configuration as code system, so that even if everything goes wrong and you didn't plan for it, you can still bring up a new cluster that more or less works as it does the other one, and then you can continue with life with not that much interruption. That was pretty much it from the learnings and operations of Kubernetes the hard way. Now we can probably go to Slido to see